All right, ABI students, Chapter 4, Lab 4, Linear Regression for Business. Now, everybody has done linear regression. Everybody. I will talk about it. I'll go over it a little bit, but everybody has done it. Master students, it was a requirement for you. My MBA students, my AIM students, you guys did this in your undergrad. You're required a certain amount of statistics to graduate from a certified university, which requires one of those things to be statistics and up to the level of linear regression or multiple linear regression. Nevertheless, I will go through this. I don't want to spend much time on this. I want to save that for the next two lessons, which is clustering, right? Because clustering will be new for everybody. But nevertheless, it's important you guys understand what you're talking about when you deal with linear regression, because in terms of both predictive, this actually falls under predictive analytics as well, but in terms of both descriptive and diagnostic analytics and predictive analytics, this is your base. This is like the baseline over here, linear regression. Everybody's taught that, right? This is where basically everything starts, if you will. So you have to basically at least be able to understand and have a conversation about what linear regression is and the results around it. Okay? So again, what is linear regression? It's obviously a statistical technique. Statistical technique to represent relationships between two or more variables using a linear equation. Number one, linear regression, it's in the name. This is a linear statistical technique, right? Linear statistical technique. And obviously we can use linear regression to predict outcomes. Outcomes for models and data that is linear. In today's lesson, we want to basically, or for this first slide, lectures 4, we want to focus on understanding linear regression, checking the model assumptions, using a simple linear regression, refining the data a little bit for simple linear regressions. I dabble in this a little bit. I don't spend too much time on it. And obviously introducing multiple linear regression. We're going to be using chapter 4 _ marketing data that I posted on Blackboard, which is a little bit simpler data set than we've been working with. All right, so let's start with first loading up the data. Chapter 4, marketing data. Go ahead, I open it up. I can leave it like that. I want to just denote the factors. I go ahead and import the data. Excellent. Let me open a new file. I will save this as Spring ABI Spring 2020, and I'll call this ABI Lab 4. All right. Okay. From here, let's load in the libraries I need. I'm going to obviously be using data.table. And I'm going to be playing around with ggplot as well. All right. And let's make a copy of our marketing data. We'll call it advert, just in case we mess up. And let us convert our table to a data table. All right, and let's check it out. Okay, it's a data table. We see that. It has 5 columns. All of them are numbers. No need to mess around with any categorical data. It seems like all of them are actually numeric amounts. They don't represent anything. So we're good there in terms of levels and all that jazz. Let's do a quick check to see if there's any nulls in our data. Right. And there is no NAs, so we have 5 number columns, no NAs. All right, smooth. Moving right along. All right, let's do a quick summary, get some summary information from these guys. Remember, the summary function gives us the 5 number summary. What's the 5 number summary? Min, first quartile, median, third quartile, max, plus the mean as well, We did this before. We'll do it again. Let me just copy and paste this. Move this along a little bit faster. Right, boom. As we can see, if you're ever confused about what's what, you can just run summary on one particular column if you want, and you can get the breakdown of what's what. Right? So basically, the first one's min, first quartile, median, mean, third quartile, max. All right? Here, the median and mean, look how the numbers are somewhat similar. Well, obviously for Google AdWords and Facebook, the numbers seem very similar. Twitter's slightly off, but what's that a sign of? Who remembers from statistics that when your mean and median are similar or exactly the same, what is that a sign of? That is a sign that your data is normally distributed. It's normally distributed. And the reason it's normally distributed, if you guys remember that famous bell curve that we see over and over and over again, the reason why it's normally distributed is because the median, unlike the mean, is not affected by outliers. The mean, though, the way math works, is heavily affected by the outliers. And because it's affected by the outliers, because if there is no outliers, then its numbers will be very similar to the median. In fact, in a perfect normal distribution, the mean and the median are the same number, right? So right off the bat, it looks like we have almost normally distributed data. And that's good in the sense because a lot of the normal distribution is the most popular distribution in the world because a lot of natural sciences and physics, natural sciences, physics, astronomy, sciences, everything involves a lot of normal distributions. It's very wild how the normal distribution works. What doesn't really follow normal distribution tends to be financial data, my world, which is why I hate normal distribution and I hate linear regression, because linear regression also works on the premise of linear data and normally distributed errors and all that jazz, which again works fantastic in the world of science, but not usually in financial data or stock data, to be specific, because who drives stock prices? Not science, human beings, and human beings are crazy. All right, so now again we have numeric data. Let's view it, right? Let's view our numeric data. And let's visualize the distribution. Now, the thing is, we want to visualize, let me show you the data right here again, right? We have Google AdWords, Facebook, and Twitter, right? All right. Now, let's say we want to analyze the distributions of, like we did for Google AdWords, Facebook, and Twitter. Because the way the data is set up is that the amount we spent on marketing in these 3 different channels, marketing channels, that adds up total to the amount we spend on marketing, and then we see how much revenue is generated from that marketing, right? But let's say we want to see the box plot. We want to see the box plot distribution of both, because we already saw the 5 number summary, but remember, the 5 number summary visualized is the box plot. So how would we set it up so that we could see the Google AdWords, Facebook and Twitter, the distribution of the numbers side by side, right, in ggplot. Remember how we did this before, right? When we wanted to compare a categorical to a numerical data, right? We basically set up the plot where the categorical data was on the x-axis and our numerical data was on the y-axis, right? But how do we do this with our advert table? Because our advert table is not really set up in that way, because instead of having all the values in one column and the labels for those values in another column, they're in three different columns. They're in three different columns. You see that? Whereas in ggplot, when you do this kind of graphing, usually you have one column that has the numerical data and another column that has the categorical data. So how would we recreate the graph like this? We have to create a new table with the categorical column, right? We have to create a new table with the categorical column, and we have to stack the data for Google AdWords, Facebook, and Twitter on top of each other. That's what we do here in this scenario right here. So the first thing I do is I create a variable for all the values of Google AdWords in G. So remember, there's no dot parentheses. This is going to be a simple vector. G, F, and TW will be simple vectors. G is the vector of all the prices. So G now has all the values of Google AdWords. It's a vector. F over here is going to have all the values of Facebook. TW is going to have all the values of Twitter. And now, what am I doing? I'm creating a new vector, NV. That's going to be the combination, that's going to be the aggregation of these three vectors. So these three values are going to be stacked up upon one another in the vector NV. That should be pretty clear what's going on here. Now, we need to create another vector that labels each piece of data according to what column it belongs to, right? So for example, let's say we only had 10 values in Google AdWords, 10 values in Facebook, and 10 values in Twitter, right? So the way, let me go to my trusty Excel sheet. Right, so just visualize it for you guys a little bit. Let me zoom in. All right, so let's say, so for example, we have the Google AdWords column. We have the Facebook column, and we have the Twitter column. All right, and it has some values. Let's assume 3 rows, just keep things simple. Right, now if you remember how how ggplot works, is when you're graphing the distributions of the box plots, remember again, comparing a numerical and categorical data is a column. It goes on the x-axis. The numerical data is another column, goes on the y-axis. So how do we graph these guys, right? I have to basically create another column. I think I called it what? NC, NV, all right. Right? I'm creating another table that's basically going to take these values, and they're stacked on top of one another. That's basically what's happened with NV. Right? And I want to put NV create a new table, data table with NV, so I can graph it. But what am I lacking? I'm lacking that categorical data, right? Forgot what I called it. Let's say, assume I called it NC. I need that categorical column. And in that categorical column, it needs to match up basically which one's a Google AdWords, which one's a Facebook, which one's a Twitter. Obviously, you guys have seen right in front of you, the first 3 are Google AdWords. The second set of 3 are the Facebook. And the last set of 3 is the Twitter. Right? You're seeing that right in front of you, right? That's basically what we need to do. And now, even if we have a table with just these 2 columns, we can now do that graph. That's the idea of what's going on here. So I created NV, my first part. My second part, yep, I called it NC. I need now that column of the names, right? And I don't have to give, you don't have to give the whole name if you don't want. I just use G's, F's, and TW's to represent Google, Facebook, and Twitter, but you can put the full name in if you want. And look how I do it. I use a C function on the outside, right? And within it, within that C function, I'm calling 3 different vectors. 3 different vectors I'm creating on the fly dynamically, right? Dynamically on the fly. How am I doing this? G, we're going to repeat G, n row G times. What does n row all caps do again? To a vector, it gives you the size of the vector. To a table, it gives you the number of rows in a table. G is a vector from up here. So therefore, this is going to be repeating G however many times there are values in the G vector. Same thing with the F, same thing with the TW, right? So now I'm going to have my NC and my NV from here. I make a whole new data table, and if you were to view the first couple of rows, this is what you would see, right? So let's go ahead and do that now. All right. So I have my Google AdWords. I have my Facebook. I have my Twitter. All right. Hold on, let me make this a little bit bigger. Make sure you guys can see this. Not too big, but all right. Okay. Now I want to do I'm going to combine this into, let me make it a little bit smaller. Maybe that's too big. All right. I'm going to combine this now into a vector name and name it anything you want. It's okay. All right. As long as you're consistent with how you're using it. Now I need to create the other categorical column, C function, and I'm going to have the 3 vectors. First vector, repeat G n row G times. All right. So that's my first vector. My second vector in there will be repeat F n row F times. And finally, my last one will be repeat TW n row TW times. All right, I got that. If you want to check out NV, boom, see that? See that? All right, and now I can create a new table called, I'll call it, it's advert2 in my slide, so I'll try to keep it consistent. And this will be literally NC and NV. All right, now I'm ready. And again, let's click it right here just so you guys can see it. Where's advert2 here? Oh, there it is. Advert2, click on this. See that? GGGs, and then it'll eventually become FFFs and et cetera, right? From here, now, what can I do? I can do my graph. I can do my graph. Right here, I don't put any color, but by all means, let's put some color in there. How do we work ggplot, guys? Table name, aesthetics, the columns I want to use. I'm using both of them. So on the y-axis, let's do the x first. On the x-axis, I'm going to put my categorical column. On my y-axis, I'm going to put the numerical data. And literally, I'm going to say, right, let's make the color, pink. All right, there you go. Now we have this on the table, so it's easier to see. right? But now visually, look what we're doing now, okay? Here's Google, G, here's Facebook, here's Twitter. All right, Facebook and Twitter pretty much cost almost the same. There's slightly more expensive prices for Twitter, and there are some outliers over here, as we can see, right? Google, it's expensive. It's expensive, magnitude-wise. Look at the magnitude-wise, how much more expensive it is. Here is the power. We've talked about this before with the Titanic data. Look how visually you can see that now. Google's expensive, man. Google's more pricey than Facebook and Twitter. And previously, you also find Google's actually more effective too. So why the hell not, right? But Twitter and Facebook are somewhat the same, but there is a higher end to Twitter, and there's a couple outlier prices in terms of paying for Twitter marketing. All right, also, they're all the data in our table is numeric. Let's use the pairs function again and see all the relationships between the data points. Now remember, okay, we're talking about linear regression, right? Linear regression is basically the mathematical model describing two or more variables. It always starts with a scatter plot. It always starts with a scatter plot, right? A scatter plot is basically, think of a linear regression as opposed to a multilinear regression. Argument to pairs. Oh, sorry. There we go. Notice advert 2 failed. Why? Because I had a non-numerical column there. Let's make this bigger. It's a little more clear here. So here we go. And right here, just like we did last time, we can see different relationships. Right here, we look for the solid lines and look for the cloudy lines. So Google AdWords and Facebook have nothing to do with each other. All right, it seems to be no relationship there. Wherever you have these clouds, Facebook and marketing total. Oh, look at this, Facebook and marketing total. All right, it's also be kind of cloudy. Let's look at the good stuff. Here, look at that solid line. What is that? Google AdWords and marketing total. Makes sense. Makes a lot of sense, right? The more we spend in Google AdWords, the more our marketing total goes up. Why? Google AdWords is much more expensive. It probably has a bigger impact on the budget. We just saw that visually, right? Where else do we see clear lines? Here, marketing total and revenues. Fantastic. What does that mean? That means that the more you spend on marketing, the more revenue you're going to have, right? That's always a positive sign when you're spending money on marketing, right? Where else do we see some positives? I guess we see a little positive over here, and that's where you see Google Words and revenue, right? We talked about this before, how it flares up. And same thing with Facebook. Facebook tends to be all over the place as well. But I guess there is a little bit of a line over here, then it starts getting kind of clouded and messed up over here, right off the bat. But then we look at Twitter. What the hell is going on with Twitter, man? There really is no line between Twitter and revenues. Again, maybe you can make a case for Facebook. How are you going to make a case for Twitter? All right. So again, that whole Twitter thing in a manager meeting, you would probably argue the case. Hey, man, maybe we should look to replace our Twitter budget we're spending on maybe Facebook and Google instead. All right, relationship between values. Let's do a deeper look. Once you have that pairs-wise analysis, the relationships that you see, we can use that. So here I do two graphs. I do one in between AdWords and marketing total and revenues and marketing total, right? So let's go ahead and do our scatter plot. If you remember, when you're comparing two numerical data points, guys, which graph you use the good old scatter plot. All right, whatever you want. Let's do the first one, be Google AdWords and marketing total. So I'm going to switch it up a little bit. X, I'll put my marketing total. And Y, I will put my Google AdWords. All right, I'm going to scoot this over a little bit. Let me do plus. It's going to be tabbed in a little bit after I do the enter after the plus, but this is just so you guys can see more, a lot more clear. And I'm going to do my GOM. Now remember, there is no scatter plot function. There's a point function. That's because you're going to place all these in dotted points, and that's it's going to create the scatter plot. So here, let me change the color. The fill won't work here because there's nothing being filled in. You have to actually use the bound, change the boundary color, and that's what I'm going to do with color. And I'm going to make this blue. And boom, look at that. Right? Nice, very nice. Look at that. Makes sense. Google's expensive as hell. It's going to have a huge impact on the marketing total. Let's do now the other one, which was marketing total and revenues. This is an important one. But this time I'm going to put revenues on X. I'll put marketing total on Y. And I'm going to make this color purple. All right, see that? Very nice, very nice. All right. Now, let's talk about simple linear regression. All right, take this step by step. Linear regressions, again, are linear models, and they're constructed using the data points you give it. We give it both the I mean, for linear regression, it's just two variables we're giving it, two data points, two columns of data, right? We're giving it one set of data that predict the value of a dependent variable, right, based on one independent variable. Oh, I'm sorry. We actually give, I'm sorry, I'm reading the wrong thing. We give it a dependent variable and an independent variable, okay? The dependent variable is the variable that we wish to predict or explain. The independent variable is a variable we're using to predict or explain the dependent variable, right? For example, let's say hypothetically, we want to basically test the fact that a person's weight makes them stronger. So we want to measure a person's weight relative to how much weight they can bench press. Okay, we're testing the hypothesis. Hey, the more somebody weighs, the more they can bench press. For those of you that have never been in a gym in your life, bench press is a form of exercise where you lift the weights off your chest. All right. So in this case, the dependent variable is the amount of the amount of weight the person can bench press. The independent variable is the person's weight. The independent variable is what you're using to try to predict how much somebody can bench, right? And how much somebody can bench is the dependent variable. You can only have one dependent variable, whether you do a linear regression or multilinear regression, just one. All right. Now, regression, in essence, is always just trying to predict the value. I hate that we're using the word predict, but it's trying to predict the value of a dependent variable based on the value of at least one independent value. Must be one, but it can be more than one. All right. And regression analysis explains the impact of changes that the independent variable explains the impact of changes to the dependent variable coming from the independent variable. Like if we were to change, if the body weight changes by 20 pounds for each individual, how much does that affect the change in the individual of how much they can bench press, right? The rate of change from the weight the weight of the person to how much weight they can bench press, right? What's the change there? The variance in those differences. Both regression analysis is used to predict or explain. Here is the formal formula or definition of a linear regression, or of a regression of any sort, pretty much. Your dependent variable is usually defined by y of some sort, right? Here we only have one. This particular equation is only a linear regression because there's only one independent variable. How do we know this? Because that's where the x is. The x's are usually defined by the independent variables. All right. And then there's two betas, beta 0, beta 1. You see this in mathematics all the time. You guys probably remember it from your stats and maths books, right? Beta 0 stands for y-intercept. That is where, because remember, we can graph this linear regression, right? We can graph this linear regression. So the question is, where do you start, where do you draw the line from? Because the line is always coming off the y-axis, right, when you're drawing the line. So I have an example here. I don't have an example here. Right here, see? It's right here. See that? Whenever we're drawing a linear regression, I don't care if it's going down or up or it's kind of straight or whatever, it always is starting from the y-axis, right? The question is, where in the y-axis should it start? That's what the y-intercept is saying, this beta 0. That's why it's called the y-intercept, because that's where the line intercepts the y. Okay? This part, beta 1, that's always attached to the independent variable. No matter, for every independent variable you'll have this other beta attached to it that has some sort of sub number greater than 0. The 0 is always saved for the y-intercept. So because we only have one independent variable, there's only one beta 1, and this is basically saying the slope of the coefficient. The slope of the coefficient. What does that mean? If you guys remember, I believe this is algebra. If you guys remember from algebra, when you have a line is defined by two things. One is defined by your y-intercept. We already talked about that. And the second thing is defined by is its slope. What does that mean? Basically, it means how does it go up or down? Does it go up really fast? Does it go up really slow? Does it go down really slow, or does it go down really fast? That's the slope. Basically, the slope, right? How high or low it's raised, pretty much. Okay? That is what right here, the dotted line. See the dotted line? Run over rise, right? That's what the slope is basically. However, this number is basically dictating what that slope is going to be. If this is a positive number, if this is a large positive number, okay? If it's a large positive number, so the larger positive number, oh, where am I? There you go. The larger positive number right here is going to mean that it's a very steep positive line. It's going to go up like, right? Think of a black diamond on the ski slope. A large positive number means a very high vertical or steepness. A low positive number means that it's going to be more and more of like a green trail or flatter, more of a flatter line. A negative obviously means the opposite way. A very high negative, a large negative slope is going to give a steep going downward. That's probably more accurate of a black diamond. Versus a smaller negative number, which is going to be going downward, but at a much flatter rate, right? So that's basically the breakdown of what these numbers mean. Now, there's another thing over here called random error term, and you see this everywhere in the world of regression, the error term, okay? What does this mean, okay? This means that when they're doing the analysis, when they're fitting the model, the linear regression model, there's going to be some error involved. Here, we have 1, 2, 3, 4, 5, 6 data points. These 6 data points are constructing a linear regression, okay? Obviously, these data points right here are the actual values. This line is going to be the estimated model of this data, okay? You notice that these points are not on the line. They're away from the line. That distance from the line is the error. That distance in the line is the error. And you notice the little subtype I there? Why is that there? It's there because once you factor in for each data, once you have the model and you factor in the y-intercept, boom. You factor in the slope, ba-boom, right? And you factor in the x values in the independent data set you gave, right? Boom, right? That'll just move along right here, and it'll move along the line. To get, that'll be your estimated y value. But to get to the actual y value, for each point, you have to add that error back. So in this case, you have an error right here, a positive error. In this case, you have a negative error, positive error, negative, positive, negative. Right? That's the whole point. That's the whole idea right there. All right, the simple linear regression equation, it's the estimate of the popular regression line is going to be interpreted like this, right? Notice the y hat versus the non-y hat. The y hat literally means the predicted value. Anytime you see this hat over the y, that's the predicted y versus the actual y, right? This is the estimate of the regression intercept and the estimate of the regression slope. Now, value, and then obviously the value of the xi. Now, why do they use the estimate of the regression estimate? Why are they using the term estimate, right? Why are they using the term estimate as to this term population, right? What does that mean? Okay, so for those of you that don't remember your stats, the science of statistics, the science of stats is based on the concept that we never ever have access to all the data. For linear regression, that's damn true because you're giving it the data you have, not every possible data, but the data you have doesn't mean you have every possible data point for whatever you're learning, whatever you're trying to model, okay? The way stats works is that theoretically, there's population data that theoretically encompasses all the data for the model you were working on. Like for example, the example I gave was, hey, the person's weight versus how much they could bench press. You technically, if you had the weight and the amount the weight for each person and the amount each person could bench press in the whole world, right? All 9 billion of us or whatever, throughout time, then you actually have the population data. Then when you calculate the analysis, right, you will actually have not an estimate, but you will have the actual intercept and the actual regression slope. But we don't have that, right? You're probably going to have a data set of like 100,000, probably, maybe even 1 million. But again, that million doesn't encompass all 9 billion or other human beings over time. So that data you have, no matter how large it is always considered a sample of the population data. And because it's a sample of the population data, again, this is the science of stats. Don't look at me like I'm crazy. This is how it's done, people. All right? Every time you calculate something from data, the data you have, no matter how big and vast it is, it's always considered an estimate. So this is why they're very careful to use the term estimate of regression, estimate of intercept, estimate or slope. That is the science of stats. All right, now, again, B0 is the estimate average of value of y, if you're interpreting the data, right, is the estimated average value of y when the value of x is 0, right? They always like saying, okay, if there's no input for x, what's the value of y going to be? That's what your y-intercept is basically saying, in terms of business speak. In terms of business speak, but I mean, sometimes it's not really coherent, but it's some sort of baseline model for if there's no input of x. Beta 1 is the estimated change in the average value of y as a result of a 1 unit increase in x. All right? This is now when we start talking about hypotheticals. If I increase my unit of x by 1, right, how's that going to overall affect my unit of y? And we talked about this as an example from before. If I increase the person's pound, how much the person weighs by 1 pound, how much is that going to increase the amount of weight the person can bench press, right? And for any of you guys that's been to the gym, you already know that damn weight has nothing to do with the bench press weight. Stupid weight. All right? Here, LM, the LM function, this, ladies and gentlemen, this is the regression function. It's so simple. It's so simple, right? I'll do the second parameter first. Here, you specify in the data parameter what table you're using, right? And then here, you To the here you have a tilde. To the left of the tilde, you put the column that you basically your dependent column, what you're trying to predict, right? And to the right of the tilde, you put your independent column, basically what you're using to do the prediction, which column you're using to do the prediction, right? And you save it at whatever variable you want here, model, whatever, blah, blah, blah. And boom, boom. It's that easy. You just did a regression. All right? All right, so let's do this, right? I'll call the model model 1. Name it anything you want. Tilde. So first things first, I'm predicting I want to build a model that where marketing total predicts revenue. Revenue, oh, it's revenues. And again, what goes first is my dependent variable, or what I'm predicting, and what goes second are all the independent variables. All right, the data is coming from my advert table, and very simple, people. Boom! It's that easy. I made a regression model. Duh! Right? Very easy. Let's see what's in it by default. All right. Very simple. It shows a simple formula right here. Nothing out of the ordinary. And it shows you your values, your immediate results. My intercept value and my slope of the marketing total dependent variable. Okay? Or the coefficient, if you will. The coefficient for marketing total. It's kind of, the value 0.05, but, is that good? Is that bad? We don't know, right? But this is the coefficient we use. That's the coefficient we use. A little interpretation game. If you didn't spend any money on marketing total, if it was totally 0, right, then your revenue would be 32, would be this value, 32 point whatever. Let's say revenues are in the thousands or in the millions, right? Whatever unit the data is written in, then this would be 32,000. If it was the units was 1,000, if it was millions, then it would be 32 million. All right, so that's basically what we get out of this. Now, here, right, if we go to the data, so it looks like our data is actually everything is in sets of thousands. All right, everything is in sets of thousands. Let's take a quick look at it. All right, so on this slide, we're interpreting the analysis, and this is where the business application comes into play. One, the context of the data matters. What is the units of the data that we are using? Like if we go here again, I have advert open right here. We see these numbers right here. Okay, what's the units of these numbers? Is it thousands? I believe that the assumption we make in the table is that these are in thousands. So this is really 65,000, 47,000, 52,000, 165,000, 39,000. Our data is in the units of thousand. That matters. When you're interpreting, the unit of the data you're using matters. Okay? So here, what does this mean? This 0.05193 means multiplied by 1,000. It comes out to $51.93. What this means now is for every $1,000 increase, remember our unit of data is in thousands, right? So this is 47,000, blah, 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 65,000, 165,000. So because our unit of data is in thousands, for every $1,000 increase in total marketing, our revenue now will increase by $51.93. That is how the slope or coefficient is interpreted now. For every $1,000 decrease, we're going to lose $51.93 of revenue, right? So every $1,000 we spend in marketing, we're getting $51 in revenue. That might be not a good trade-off in terms of how much money you're spending in investments, right? But nevertheless, that's how you interpret it, right? When the marketing expenditure is 0, like I said before in the slide before, right? when it's 0. If you spend no money on marketing, then the revenue will be $32,000. That is what the model is interpreting. That is what the model is implying, right? From here now, given this, we can actually start making a prediction, all right? If I spend, this is my model right here, right? This is my model right here. If I break it down, here's the intercept, here's the coefficient. If I put some hypothetical marketing total in there, I can now predict the amount of revenue. Okay, let's graph that linear regression. Let's graph that line. We can add it. We already have the scatter plot, revenues and marketing total. We already have that, okay? But now let's put in that linear regression line. And all we do, and this is, remember, I said ggplot is made for analysis, right? All we do is add another layer on top of it. And that layer we're going to add is this new line called GEOM underscore smooth, right? Let's go ahead and do that. GEOM underscore smooth. Method equals LM. Method equals LM for the linear model. All right. And it goes ahead and it adds this little line, and you can see this little grayish area around it because it shows you how much error there was when it was doing that analysis. Okay. I already have that graph ready to go right here. And I'm just going to add to it another layer called smooth. If I just did this part right here, right? Notice what's happening there, right? Notice what's happening. Look what you see. It puts a line in there, but it's doing its best to try to reduce the errors and follow the plots, right? But if we say, no, give me a line that's from using the method of linear regression, boom. Now we have our linear regression line right here. Okay? All right. Now, before we make a prediction, hypothetically, put any number in here, and that model will give you the revenue, right? Now, before we make a prediction, all right, we need to do something. We need to first see if our data satisfies 4 core assumptions. Really 3. There's one that we're not going to really do mathematically. We're going to do more of a logic test than anything else, right? Because it's a little more difficult to test that assumption. I mean, you can test it, but it's more mathematical. So it's beyond the scope of what I want to talk about in these slides anyway. But we're going to do something called looking at the diagnostic graphs. That term, if anybody here has ever used Tableau, right? Tableau has it literally has a button, print out diagnostic graphs or view diagnostic graphs. That's really talking about linear regression. So seeing if the data is satisfying the core assumptions for linear regression, right? It's used everywhere. I mean, it's pre-built in a lot of statistical packages and softwares, looking at the diagnostic graphs. And that's what we're pretty much talking about here. Those quote-unquote diagnostic graphs allow you to see if your data is satisfying these 4 core assumptions called LINE. The acronym is LINE. Linearity, independence, normality, and equal variance. And if your data satisfies these assumptions, then that's one step saying, yes, you know what? You can use a linear model. If your data satisfies these 4 assumptions, go ahead and use a linear model to build some sort of predictive model off that data. All right, so let's start off with the first assumption, linearity. Real easy how we're going to test that, right? Linearity is basically is if the relationship is linear between the predictor and the response variables. All right, one easy way to do this is just throw a scatter plot up there. If you have a scatter plot like this over here, that's really cool, but it's not linear. One down here, that's also really cool. Again, not linear. It's failing the linearity test, right? These are also, right here, failing the linearity test. Why? This one is obvious. This is a bunch of clouds we're drawing a line through, right? There really is no linear relationship. There's no relationship, period, in this one. But look at this one right here. This one, we have some nice tight data points, and we have this line going through it. You're thinking to yourself, oh, okay, all right. Nah, this also fails the linearity test. Why? Because there is no linear relationship. You see how it goes straight right across? This basically what we're saying is the more we increase x, it has zero effect on y. There's no relationship, period. That's what this is saying. There's no relationship, period, between x and y. So that also fails the linearity test. How do we test that? Again, just do a scatter plot and you can eyeball it. Independence now. Now, I don't have a really cool, I don't really have a cool graph to test independence because independence is a little more complicated, a little more complex, right? When we talk about independence, we're basically saying, okay, is the relationship between the variables independent of one another, right? It's a very difficult assumption to test. Typically, you handle this by understanding, if you could apply like a level of common sense to this, right? The current data uses data from different locations, so it's safe to say that the data from one location has no effect on the data on the other locations, right? An example of data that wouldn't meet the independence assumption, that's probably easier to see it this way, would be a table that has a variable of income, age, and occupation, right? Here, there's probably some dependence between a person's income and a person's age or occupation, right? If you had a table like that, there, it makes more sense. For example, the person's profession, right, in the one column tends to affect the person's income in the other column. This is a violation of independence between the columns, right? You see this a lot in these independent violations in data that has time series, right? Think of stock prices or think of weather patterns according to time, right? Those tend to be influenced by the previous time. This is, I say we will deal with this in time series in chapter 6. I don't think we'll get to it because I should change this because I don't get to time series in these slides. I actually skip time series because you actually have another class that dedicates the whole class is time series, right? So I skipped this so I could squeeze in R shiny and stuff like that. So independence, for the case of our class, the scope of our class, we leave it more to common sense. There are mathematical techniques you can use to test for independence, right? And again, in more advanced classes, definitely in your time series class, you guys will address this. All right, let's move on to the next one is normality. Okay, what is normality? So remember before we talked about the variables? Capital Y is the different the different dependent values, right? The actual values. And Y with that little hat on top, that's the estimated Y. That comes straight from the linear regression model. There's obviously going to be a difference. There's some error because this is a straight line where this is the actual data. The difference between the two, let's go back a little bit. The difference between the two, right, so this is Y, and the equivalent Y over here would be the Y hat. The difference between the two is that error point, right, like we talked about before. Okay? Now, these residuals, and this is important, they form a normal distribution around the regression line with a mean value of 0. Now, look, obviously my undergrad was comp sci and economics, whatever, but I did a master's in quantitative finance. I did a freaking PhD, all right? This part, I was like, what the hell are they talking about? The residuals form a normal distribution around the regression line with a mean value of 0. What the hell are they talking about? This is what they're talking about, okay? This is what they're talking about. The errors, and this is important. If you look here, let's use this line again. The errors. When you do a regression line, it's imperative that regression line, the model, the way it works, is it tries to slice a straight line through the centermost point of all the data points. That's what it's trying to do here. If it's doing that right, it's going to have data points above and below it. Above and below it, okay? We said already that the distance between the actual data points and these lines is the error for each individual data point. 1, 2, 3, 4, 5, 6. So 6 data points, 6 error points. There's going to be errors above the line. There'll be errors below the line, right? But if this regression line is done successfully, the amount of errors above and the amount of errors below will cancel each other out, so that if I were to take the average of all the errors here, this error here, this very tiny error here, this error here, this error here, this error here, and that little error there, the average of these errors would give me the value 0. Why? Because this above the line is positive, below the line is negative. Above the line is positive, below the line is negative. And if it is truly slicing that data in the middle, then the average, there should be almost equivalent amount of positive and negative errors. And in aggregation, they should be of the same magnitude up and below. And so the average should be 0. So that answers the first part, what they're saying. That basically explains the first part, that, hey, the residuals should have a mean value of 0. So what do they mean by form a normal distribution around the regression line? Why should it form a normal distribution with a mean value of 0? And by the way, a normal distribution with a mean value of 0 is what kind of normal distribution? You guys should know this from stats. What kind of normal distribution? That's right, a standard normal distribution. A standard normal distribution has a mean of 0 and deviations of 1 unit. Okay, if you don't remember that, I guess we'll go over it in Q&A. Ask me in Q&A, we'll go over it a little bit more. I'll talk about it a little later on the slides. All right, so what does it mean by normal distribution? Well, what that is saying is this, all right? Let me first get a bell curve up for you. All right, let's take a look at a normal distribution, standard normal distribution. Check out this image right here. This is a standard normal distribution, all right? So already, hopefully you understand what I mean by the error terms. Those error terms should have a mean value of 0. But why should they form a normal distribution? Okay. The way the normal distribution works, again, this should be a review for you guys, right? The center point is the mean, and then from the center point to the left goes your standard deviations in units of 1, because it's a standard normal distribution, negative values. And your positive values go this way, right, to the right. Again, in increments of 1, because again, it's a standard normal distribution. Now, let's say, hypothetically, right, come back here, we have this graph linear regression model right here, okay? So when you're making that linear regression model, you're trying to slice it through the data points. Well, guess what? You're trying to slice it through the data points in the centermost point. If, by definition, you're slicing it by the centermost points, that means the most points are around the linear regression. You have more points around the linear regression than are not around the linear regression, okay? What is going to be the error terms of all these points around the linear regression line? You're very close to the line. They're virtually 0. They're either, a very small number or close to 0. And there should be a lot of them that are 0. A lot of them should have an error term around 0. Notice what I'm saying. A lot of the data points should have an error term around 0. So if we're graphing all the error terms, around 0, you should have the most error terms. Your values that are either 0 or around 0, the error terms, if we graph the error term as a density curve, it should look something like this. Majority of the error terms should aggregate around 0, which is why you have this mountain peak over here. And as you go away from here, as the error term increases both from a positive point of view and the error term increases from a negative point of view, those numbers of error should be less and less and less. thereby producing something that looks like a normal distribution. You get it? That's why you don't get it. But anyway, but that's why, right? That's why normality is testing that property, that's testing those properties, that the residual forms should be a standard normal distribution and around the regression line with a mean value of 0. That's what that means. And damn it, that confounded me in my master's program. All right? Now, like in our previous programs, right? In our previous lessons, I'm sorry, we can use the histogram to view the distribution of the residuals. Literally, we can take the residuals, we can graph it as a histogram, okay? And the histogram should basically look like a normal distribution for us at that point. Because what is a histogram, right? What is a density curve? A density curve is a normally distributed, what is a normal distribution? A normal distribution is an equally distributed normal distribution. It's a density curve that's distributed normally, right? I really didn't say anything, I'm sorry. But what's a histogram? A histogram is basically, it's like a density curve, except its widths are larger. As the widths of a histogram approach smaller values, it starts to look more and more like a density curve. So we can use the histogram to plot it and see if it's to plot the error residuals and see if it's if it looks like a normal distribution, right? Another cool graph to check normality is the normal quantile graph, or the stat slang term is Q-Q plot or QQ plot. The QQ plot is a scatter plot of the residuals of the models versus the z-scores of those residuals. Okay, is the scatter plot of the residuals versus the z-scores of those residuals. But where do we get the residuals from? Remember what a z-score is, guys? A z-score is, again, from your normal distribution stats, normal distribution classes. A z-score is basically when you take a number, from a data set of numbers or a column of data, and you subtract the mean from it and divide it by the standard deviation. You convert it into a z-score. Why would you do that? Because that's how you fit any kind of data point into a standard normal distribution, right? When you want to fit data into a standardly normal distribution, you always convert it into their z-scores, and then it should fit if the data is normally distributed. Because then once you subtract all the data points by the mean and then divide by the standard deviation, then if you take the average of any of that column of data, it'll be 0. And the standard deviation will be 1. Right? That's just a little mathematical trick we use in stats. Right? So that's what we call the z-score. If we take the residuals, if we take the z-scores of the residuals and graph it against the residuals themselves, right, in a scatter plot, right, it should give us a line. It should give us a line. Okay, it should give us a line. Now, how do we graph something like this? Well, first of all, how do we do the histogram graph? How do we do the QQ plot graph, right? The model we made, model 1, that regression model 1, it has all the data we need in it, all right? It obviously has the residuals. It has the residuals. How do we get at it? Right there. If you run the str command on it, oops, it's kind of big. Hold on. Let me just make the screen a little bit smaller. So you get a lot of things back when you do str model 1, right? The first couple of things you see, the dollars, the dollar signs, there's a lot of data there. Lots of data. Is the residuals. See that? The coefficients, the residuals, a lot of these values are sitting there for you to check out. So literally, right, if you want to get the residuals, I simply just call the model. Right, maybe it's easier if I click on, there you go. And it basically shows you everything there. This is much easier to look at. You have the coefficients there, you have the residuals there, you have all these other things called effects, fitted values, and all these other fancy terms, right, from regression. Okay, so here if I do model 1, dollar, right, and when you do dollar, just like your tables before, all the values there, all the different sub pieces of data are all there for your use. residual. I'm going to click on the residuals part. Boom. I have all the residual values, right? The first residual value, the second data. So these 1, 2, 3, 4, 5, 6, 7, 8, these numbers you see on top of those residuals, they're basically just labeling this is the first data point, the second data point, the ordering it was in the column. All right, the ordering it was in the column, basically. The first value in the column, the second value in the column, et cetera, et cetera, et cetera. So that's how I get my residuals. All right. All right. Now, again, the problem is to do both graphs, you need we need a table, right? So that's not a problem. We can create a data table. We can create a data table with just one column. It's not a problem, right? And we don't need to go ahead and calculate the z-score. Well, I mean, we obviously can. We have functions to do it. Because ggplot, because it's awesome, will do it for us. All right? So let's go ahead and rock this. Let's do the histogram graph first. All right. So first thing I'm going to do is let me create a data table. I'll call it restdf. In my slides, I call it restdf. So restdf equals data table. Now let me make it bigger so you guys can see it. Sorry. Oh, that's too big. All right, that's bad. Just right. Data table. And I'll give it a column name. What do you want to give the column name to be? Let's see, in my slides, I gave a name. Okay, RES. All right, fine. RES equals model 1 dollar residuals. All right. And again, when you have a table or a data container of any sort, when you type in dollar, it gives you either, if it's a table, it gives you a list of columns. In this case, it's what we call a list, right? A list is a special kind of data container in R. A list, you see that right here, a list of 12. A list is a data container of data containers. So you know how we have these data containers that store values? Well, list is a data container that holds other data containers. So when you do dollar, you're basically seeing all those little data containers inside model 1, and you can grab the data container you want. In this case, we're grabbing residuals, which is like a vector. So I take this, I execute it, I have my RSDF table now. I'm going to click on it to see, boom, see? Simple data table, one column with all the errors. Those are the errors, by the way, right there, man. All right? From here now, I can go ahead and I can do my histogram. And I'm going to do my histogram. ggplot. Because I'm doing a histogram, I only have an x-axis. And that value will be the only column in there, RES. Histogram. All right, I didn't give anything, so by default it picked its own thing. It picked bins to be 30. So it picked 30 bins, okay? 30 bins. All right, let's do 10 and make it a little bit fancier. Let's make 10 bins. I'm running out of space. Let me press enter so I have more space. Fill equals purple, and the outline will be black. All right, then look at this. Right, we got a little missing data over here, so it seems like a little bit of an outlier, but overall the shape looks like what, guys? The shape looks like a normal distribution. You see that? And not only that, but I mean, I think it's kind of hard to see here. I don't know if I make it big enough over here, but if you guys look in your graph, right, what is the majority value, people? Majority of value is around what value? 0. 0, right? And we can confirm this. Let's simply take the mean of the residuals. What is it? Well, I mean, it's something called 4.05 blah, blah, blah to the power of negative 10 to the 17th number. Negative 10 to the 17th number. So it's virtually 0, okay? Virtually 0. It's like literally me writing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 0.0558. That is 0, guys. All right. So the mean is 0. And if we look at the standard deviation, oh, standard deviation is 3. Standard deviation should technically be, I mean, it doesn't really have to be, but for a standard normal distribution, the standard deviation should be 1. So here, it's violating that, but that's fine. That's fine. I mean, that's not a necessity. That's definitely not a necessity. It doesn't have to be 1. But a standard normal distribution graph has a mean of 0 and a standard deviation of 1 units. But again, as long as it has a mean of 0 and it's normally distributed around the 0, it's fine. It's fine. It's holding up, right? The results are definitely holding up. So this graph, this diagnostic graph, looks fantastic, all right? Even though it has a little bit of outlier on the right side. Now let's do the QQ plot, right? And again, I don't need to calculate my z-scores. I don't need the other column because now we're using a more fancier part of ggplot, one that actually does the stats right in it. And this is really cool. This is really cool. All right. So here, let's take the first part again. The first part is the same, but it's slightly different now. I have aesthetics, but now I'm not deciding an X or a Y. I'm saying sample equals residuals. Why am I doing this? I already talked about this before, all right? Why am I doing this before? Because once you enter the world of stats, people, once you enter the world of stats, right? All the data points you use now are considered sample data points because by default, the science of statistics, if you're is that you're taking a subset of the data, a sampling, if you will, and you're applying some sort of analysis to that sample of data to try to explain the greater population from where that data was generated. Okay? So here, sample equals res. So once you sample already, right off the bat, ggplot knows, okay, you're trying to do some statistical analysis right here. Plot. Now, I'm going to use a new type of graph that starts off with stat. Okay, that starts off with stat. Stat underscore QQ. Right? I don't need the color if I don't want it. Right? If I just do this part right here, look what you get. All right? Now, what's happening here? Why is this a big deal? This is a big deal because what happens here is your graph, right? Your error residuals, right? Remember, it's error versus your z-scores. Notice down here, your z-scores are now have a distribution. It looks like they're moving in increments of 1 in the x-axis. That's because z-scores again have an average of 0, a mean of 0, and they do have a standard deviation of 1. They do have a standard deviation of 1. Okay? Whereas up here, our samples, again, our error terms, they do have an average of 0, but we saw that it moves in standard deviations of like 3 or something like that. Okay? So where did these z-scores come from? Well, stat q underscore qq, what do you think this means? QQ plot, guys. QQ plot. Automatically, it knows, okay, this is the sample data. Cool. I'm putting the sample data on the y-axis. On the x-axis, I'm putting the z-scores. And it calculates the z-scores behind the scenes, right? We can go ahead and make this a little bit. I used to have a quant I used to work for. He always used to say, Waj, make the graphs look better. So make the report look better. So here I go. Make it look better. I guess I'll use blue, whatever. So now I have this blue line. Now, how does this work? This graph works. Well, if you have perfect normal distribution, then your scatter plot should be a perfect diagonal line. How do we know what that diagonal line is? Well, we add it, baby. Right here, we have another function that says QQ underscore line. Give me the, and this is basically the ideal line. This is basically the ideal line. All right? And that's what this function is doing. It's just basically adding that solid line that gives you a perfect normally distributed error term. Perfectly normally distributed error term around 0. Now, from this point to this point, that's fantastic. That is like right on the money, right? Here kind of fails. Here it fails, and we got an outlier over there, right? So on the edges, this kind of fails, and we saw that before with the histogram. We see even more clear over here. But overall, majority of the data, it's on that line, solid. These error terms, you know what? They're passing the term. So using both tests, we're confidently saying, you know what? Normality, the assumption of normality is holding. The error terms have an average of 0, and they're normally distributed around the mean 0, right? And we see that both in this, using the ggplot and the histogram over there. Fantastic. All right, now the last test, equal variance. All right, the equal variance test, again, it deals with the residual forms. And basically what it's saying is that there should be no there should be no pattern to the residual errors, right? And we discussed why there should be no pattern to the residual errors, because the errors, right, should basically have a mean of 0, and they should be all equally distributed as much as possible above and below that regression line. If they're not, right, that means there's some sort of pattern in pattern in the error term, right? This model, we visualize it by plotting the residuals against the predicted values of the model. So you put, again, the residuals, it's a scatter plot you're doing. You put the residuals on the y-axis, and the predicted y values you put on the x-axis, right? The predicted y values you put on the x-axis. Now again, what is this showing? What is this showing? You want a solid horizontal line, like we see right here. We want a solid horizontal line going through that scatter plot. Why? Because like we said before, as the predictions increase or decrease, it has 0 effect on the errors. As the prediction values increase or decrease, it has 0 effect on the residuals. This is, again, showing that, oh, fantastic, the data was actually, sliced somewhat evenly through the data set. But more importantly, what it's showing is there's no relationship between the prediction values and the error terms. You see, the only way you can have a relationship of some sort between the predicted y values and the residual values is and the residual errors. The only way that's possible is if the data has some sort of inherent pattern in it, guys, right? It's only if the data has some sort of pattern to it. Let's go here. Here, check this out. If I had a straight line going through here, right? If I had a straight line going through here, right? Then my predicted y values at one point, let's say I had a straight line going like from here, right here, right? Or right here, whatever, right? So what would happen is, as I follow the line and I increase my predicted y value, right? Am I increasing the predicted y value? What's happening to the error term? It's increasing as well, right? You see that at a certain point, it's increasing as well. That's showing that, hey, these data points have some sort of pattern that's not linear, and it's not linear because here, if we were to put a diagonal line right here, as my y is increasing, my predicted y is increasing, so is the error term. And we can see that. And at one point then, it would stop, and then it would start going down. Right? It would stop, and then it would start going down. At this point, as the y increases, the error term starts going down. There's a clear relationship there. And that would be seen here. But because there's actually nothing going on, it's a flat horizontal line, there's no relationship between the y and the residual data, we have equal variance, right? We have equal variance, right? And therefore, there's no relationship between the predicted y and the residuals, and there's no inherent pattern in that data that's nonlinear. And that's what we call the equal variance test, guys. The equal variance test, right? And again, you tend to have, if you have patterns, certain graphing patterns, certain time series data, you'll see it be violated here. This is where it would be violated. Okay? So if I run, okay, so I'm already I'm looking at the video time limit, so I guess this is a great place for us to stop. I'll show you one more thing. I'll show you, there's a lot, I mean, actually this is a great place to stop because this is where we'll pick up in the next video. So if I run summary on the summary command on my variable, right? You see here, it's probably easier to see over here, you get a whole mess of data back, guys. You get a whole mess of data back, and it's saying something. You got your residuals. It's giving the distribution of the residuals, right? The 5-number summary. It's giving you your coefficients, right? Right, it's giving you your coefficients right here. And then the standard errors, then the t-values, then the probability that is greater than, the probability that the t-value is greater than a certain value. What does all this stuff mean? Well, you guys know what all this stuff means because this is a review. Nevertheless, we will talk about this. We'll start off the next video on this, all right? All right, guys, I'll see you in the next video. Part 1 of Lab 4 ends at this point now.